Okay, today we will discuss some of the important problems on the stress concentration. Okay, so before discussing some of the important problems on stress concentration, first, once again, we will understood the brief introduction regarding the stress concentration and what is meant by stress concentration factor and all those things. Okay, the stress concentration is nothing but the concentration is defined as the stress concentration is defined as the concentration or a localization, the concentration or localization of a stresses in a member either due to change in change in cross section or due to change in cross section or due to irregularities in the member. Okay, so this is what this is why the stress concentration will going to takes place in a member either due to change in cross section or due to irregularities in a member. Okay, this is what the stress concentration. Okay, so usually the stress concentration will occur in a member due to irregularities. For example, is there any geometrical discontinuities such as holes, notches, fillets, grooves or threads, whatever it may be. Okay, and also it should be like internal defects such as cracks, voids, etc. Okay, due to that also, and also there is a load discontinuities and also some material discontinuities. Okay, these are some of the important the causes of the stress concentration. Okay, apart from that, here we need to discuss one more very important factor. Okay, it is very useful for the problems called the stress concentration factor. Okay, the concentration concentration the stress concentration factor. Okay, the stress concentration factor which is defined as the stress concentration factor which is defined as the ratio of the stress concentration factor is equal to the ratio of maximum stresses, ratio of maximum stress to the minimum stresses or nominal stresses. Maximum stresses to the nominal stresses. Okay, so this is the stress concentration factor. Okay, the stress concentration is measured by the stress concentration factor. It is defined as the ratio of maximum stresses to the nominal stresses. Okay, as a ratio of maximum stresses to the nominal stresses. This is, we will call it as a stress concentration factor. Okay, the stress concentration for different loading condition for axial and bending load, the stress concentration factor K sigma is equal to sigma max divided by sigma nominal. This is for the stress concentration for axial as well as the bending load. Okay, if you go for torsional load, the stress concentration factor for torsional load stress concentration factor Kt is equal to Kt or K tau is equal to tau max divided by tau. Okay, tau max divided by tau. Okay, this is the stress concentration factor for the torsional load. Okay, torsional load. Okay, k tau is equal to tau max divided by, okay, maximum shear stress divided by tau shear stress. Okay, so this is what we will call it as a, okay, stress concentration factor for bending as well as axial load and torsional load. Okay, so this is the definition for the stress concentration, axial and bending load, and for the torsional load. Okay, same way stress concentration factor for normal stresses, for nominal stresses, nominal stresses for axial load, sigma nominal is equal to F by A. For bending load, sigma nominal is equal to mb by I into C. Same way for torsional load, sigma nominal is equal to mt by J into C. Okay, maximum bending moment, maximum torque mt. Okay, and J is nothing but a polar moment of inertia. Here I is nothing but a moment of inertia, where F is the direct load or axial load, A is nothing but a cross sectional area of that given member. Okay, so this is the stress concentration factor and the definition for the stress concentration. Okay, so stress concentration is occurred due to change in cross section or due to irregularities in the member. Okay, this is what stress concentration. The stress concentration factor is defined as the maximum stresses to the nominal stresses. Okay, it is a ratio of maximum stresses to nominal stresses. Okay, for stress concentration for axial and bending load, okay, this is a k sigma is equal to sigma max divided by sigma nominal. Okay, for torsional load, k tau is equal to tau max divided by tau. For nominal stresses, for axial load F by A, for bending load mb by I into C. For torsional load, okay, sigma nominal is equal to mt by J into C, where C is nothing but a d by 2. Okay, d by 2. This is what the stress concentration. Apart from that, okay, here we have, okay, two factors. Okay, so two factors in the sense, okay, for example, if you go for this one, okay, the k sigma as well as or k tau. K sigma or k tau is the theoretical stress concentration factors. Okay, k sigma or k tau is the theoretical stress concentration factors. These two are depends on, okay, these two are depends on the type and size of the discontinuity. Okay, type and size of the discontinuity. But okay, the k sigma A is the actual stress concentration factor. K sigma A is the actual stress concentration factor. It is depends on the material. Okay, and type of loading, and it's different from theoretical stress concentration factor. Okay, k sigma or k tau, these two are the, okay, theoretical stress concentration factors. It is depends on the size, okay, type and size of the discontinuity. But okay, but k sigma A, okay, k sigma A is the actual stress concentration factor, which is mainly depends on the type of material and type of loading. It is completely different from the theoretical stress concentration factor. Okay, completely different from the theoretical stress concentration factor. Okay, so usually the relation between the theoretical and actual stress concentration factor, okay, the relation between theoretical and actual stress concentration, actual stress concentration factor K sigma A is equal to 1 plus Q into K sigma minus 1. Okay, this is the actual stress concentration factor, where Q is nothing but a notch sensitivity or index sensitivity. Okay, where Q is equal to notch sensitivity. Okay, or index sensitivity. Okay, this is the relation between the theoretical as well as the actual stress concentration factors. Okay, theoretical as well as actual stress concentration factor. Okay, where Q is the notch sensitivity or index sensitivity. Okay, so this is some of the basic information regarding that stress concentration. Okay, by using these things, okay, we can solve a number of problems on this. Okay, now we will discuss one problem based on the stress. Okay, now we will discuss some of the important problems on stress concentration factor. Okay, so generally first we will understand the given problem. Okay, a notched flat plate as shown in figure, okay, as shown in below figure, is subjected to bending moment of 10 Newton meter. MB is subjected to bending moment of 10 Newton meter. Determine the maximum stresses induced in the member by taking the stress concentration to account. Okay, so this is a given figure. Okay, this is a given figure. The figure is subjected to a bending moment of 10 Newton meter. Okay, this is a 10 Newton meter bending moment. Here what we need to determine? We need to determine the maximum stresses induced in a member by taking the stress concentration. Okay, here what we need to find out? We need to find out the maximum stresses. Okay, first we need to find out the maximum stresses, then we need to find out the maximum stresses. By using that we need to find out the stress concentration. Okay, stress concentration, then we will find out by using the stress concentration factor, theoretical stress concentration factor, then we need to find out the maximum stresses. Okay, let us first note down the given data. Here what is the MB, maximum bending moment, which is 10 Newton meter, 10 Newton meter. So you can convert that into Newton millimeter. 10 into 10 to the power 3 Newton millimeter. Okay, what is the diameter? Diameter of this flat plate, D is equal to 60 mm, and R is equal to the radius, R of this notch, it should be 10 mm. What is the thickness? HRT is equal to 10 mm. Okay, this is the given data. Okay, this is the given data. Here what we need to find out? First we need to find out the small d. Okay, for that we have a equation, d is equal to capital D minus 2r. D is equal to capital D minus 2r. Therefore d is equal to d plus 2r. By using this, okay, if you substitute the values in this equation, where capital D is 60 minus 2 into what is a small r? Small r is equal to 10 mm. If you simplify this, D is equal to this diameter. Okay, this diameter D is equal to 40 mm. D is equal to 40 mm. D is equal to 40 mm. Okay, here what we need to find out? Okay, here we need to find out sigma max we don't know. Okay, for that what we need to do, K sigma is equal to sigma max divided by sigma nominal. Okay, sigma nominal. So what is the sigma nominal here? Due to nominal stresses, sigma nominal is equal to with respect to maximum bending moment, here bending stresses, okay, mb by I into C. Okay, mb by I into C. What is the K sigma C? Okay, so here R by D plus D by D. By using these things we can find out. Okay, here what our ultimate intention is, okay, this is the one we need to find out. We need to determine the maximum stresses induced in a member by taking the stress concentration into an account. Okay, this is what we need to find out. Okay, so then what we need to do, okay, from figure 4.25a, from figure 4.25a, from new design data handbook, okay, new design data handbook, the figure should be like this. Here we have R by D and here we have the K sigma stress concentration. So from figure what we need to find out here, we need to find out the R by D as well as capital D by D. R by D, where small R by D ratio as well as D by D ratio, okay, to find out the stress concentration. Okay, so if you substitute that R by D, we know small diameter, okay, small diameter is 40 mm and we know the value for R is equal to 10 mm, okay, 10 by 40 we will get 0.25, will get 0.25. If we substitute the values in this ratio, so 60 divided by 40, we will get 1.5, okay. For example, you can see here we have R by D ratio and here we have the stress concentration, okay. The R by D ratio, what is the R by D ratio? Here somewhere we have, okay, 0, 0.5, 0.15, okay, 0.10, 1.5 like that, okay. So here somewhere it should be 0.25, okay. So it should be just, you just extend the line and you just, okay, up to here. This is the D by D ratio, which is 1.5, okay. Somewhere here it is 1.5 line, okay. Up you extend this line up to this line, okay, where exactly it will coincide, you just draw one more line, okay. So here what you will get, you will get the stress concentration factor called K sigma, which is 1.575, okay, 1.575, okay. This is the theoretical stress concentration factor. K sigma is equal to 1.575, okay, 1.575. This is the stress concentration factor, okay. Here we know that, okay, so here what is the type of nature of the load, okay, the nature of the load is bending, okay. So here the maximum bending moment, here what we need to determine the maximum stresses induced in a member, okay. So here what is the nature of the load? Nature of the load is bending, okay. So the bending moment they have given, okay. For that what we need to do, okay, for bending load, for bending load, okay, for bending load, sigma nominal stresses mb by I into C, mb by I into C, okay. Here you can see here what is the value, okay, where I is equal to moment of inertia, okay, from the design data handbook, you can refer that value, okay, equation. Here we have, okay, BDHT cube divided by 12, okay. So, or this one we can write it in terms of BH cube divided by 12, BH cube divided by 12, okay, where C is equal to small d by 2, where C is equal to small d by 2. Okay, this equation, it is available in the design data handbook, or you can directly remember. Okay, so where I is equal to HD cube divided by 12 or H or B. Okay, so you just replace the H, okay, you just replace B in terms of H or H in terms of B, okay, with respect to the nature of the problem. Okay, here if you substitute that values, okay, into this equation, we know that maximum bending moment, okay, which is MB, okay, it is given in the problem called 10 into 10 to the power 3 Newton mm, okay, 10 into 10 to the power 3 Newton mm, okay. You can see here, if you substitute that values, okay, into this equation, 10 into 10 to the power 3 divided by, what is the I, okay, we know the value for H, okay, 10 into d cube 40 cube divided by 12, okay, if you substitute that values, 10 into 40 cube divided by 12, we know the value for C, where C is equal to d by 2, okay, 40 divided by 2, so it should be 20, or you can directly write it 40 by 2, 40 by 2, okay. If you simplify this, whole term, okay, sigma nominal, okay, with respect to bending load is equal to 3.75 Newton per mm square, okay, 3.75 Newton per mm square, 3.75 Newton per mm square, okay. This is what we need to find out, okay. Here we know that B or, here don't get confused with B or H, okay. So here B is equal to 10 or H, okay, H is equal to 40, that is equal to D, okay. Here it should be breadth, okay, it should be height, okay. So you just leave it this, okay. So this is what we need to find out, that sigma nominal, okay. Why we need the sigma nominal, okay, we want to find out that maximum stresses. What is the stress concentration factor here? Case here we need to consider the stress concentration factor into an account, okay. K sigma is equal to sigma maximum divided by sigma nominal, sigma maximum divided by sigma nominal, okay. We know the value for K sigma. What is the value for K sigma? K sigma is equal to, okay, by using the figure number 4.25a from the design data handbook, okay, with the help of R by D as well as D by D ratio, we will find out K sigma. K sigma is equal to 1.575 is equal to, we don't know the maximum stresses and we know the nominal stresses, okay. What is the nominal stresses for with respect to bending load, okay. By using this equation MB by I into C, we will get the nominal stresses of 3.75, okay, 3.75 Newton per mm square. If you simplify this, sigma maximum is equal to 5.906 Newton per mm square, 5.906 Newton per mm square, okay. So this is the, okay, objective of the problem. This is what we need to find out. This is the maximum stresses induced in a member, okay, by considering the stress concentration factor into an account, by considering the stress concentration into an account, okay. The maximum stresses is 5.096 Newton per mm square, okay, Newton per mm square. This is the problem, okay, very important.